Welcome to another exciting digital design class. In our last digital design class, we were doing new material because nobody had any questions about the midterm, which is due next week. And so what I thought I would do, just because I'm a nice guy, is reopen the floor to any questions that you might have about the midterm now that you've had a chance to look at it a little bit more carefully. Yes. Okay. What's your question? Does it have to be quickly? Maybe I could just take my time and do it? Okay, that's good too. All right, so what do we got? I think we need a new sheet of paper. Or I could do it really quick. If I do it really quick, I can drink coffee and talk fast. So let's see. Number 7. Number 7. It says A, B, or A, B, C prime. Okay. Suppose there is any one of a number of different interesting and wonderful ways to do a simplification like this. Let's start by writing a truth table. Oops. Now, it says here, f will be true if a and b are both equal to 1. So that's going to be here and here. It says f is going to be true if a is a 1 and bc inverted is going to be true. Now, if I took a, b, c inverted and wrote it out using De Morgan's theorem, it would be a times b prime or c prime. I can simplify that by cross-multiplying a b prime or a c prime. Everybody kind of see that? So now, if a is a 1 and b is a 0, f will be true. So I look for the pattern 1, 0 here, and I see it here. Here I see if a is a 1 and c is a 0, it will also be true. But we already have that there. So now, everything else is 0. Everything below this line is a 1. Everything above this line is a 0. If you really want to do this formally, you do a K-map. Number your truth table. And note that f is going to be true for elements 4, 5, 6, and 7. Everywhere else it'll be a 0. Now you do your looping. And what do you call that product term? Yeah, that's A. And you can see that when A is true, F is true. So we've replaced F with a wire that connects to A. Can't get simpler than that. And so that is a correct answer to question 7. And the way I approached it, which was very methodical and correct, you could have skipped it, skipped steps, done a whole bunch of other stuff. But what I did here, which was really, I think, the right methodically correct thing to do, figure out where f is going to be true in the truth table, get your k-map, loop your k-map, and that'll give you a minimal form. And that will, you know, while here it may have been overkill, that will always work. Any other questions about the midterm? Sure. Okay. So 25 is showing a 3-element vacuum tube. The 3 elements are the cathode, the grid, and the plate. Because there are 3 elements, it's called a triode. If there was only 2 elements, no grid, we would call it a diode. The question, what is the question? Which of the following are true? Can the triode be used as a switch? And the answer is yes. Yes, it can. And in fact, if we think about it, the first general purpose programmable electronic computers were done using vacuum tubes that had triodes in them, just like this. And that would be the ENIAC, for example, or the EDSAC, or the BINAC, or the SEA, the SEAC, or the MANIAC. It was a MANIAC. And in fact, there were a whole bunch of ACs. Why were they all called ACs? I guess because ENIAC started it, and then they all just built on it. But ENIAC was kind of like the progenitor of all the other ACs. All tubes all the time, 1,000 times faster than relays. In fact, if you had thyratrons, which were tubes that were tuned for switching, they could run at 500 kilohertz, which is way faster than relays can switch. So these were considered state-of-the-art devices at the time. 1908. DeForest decided to use this device not just to act as a switch in saturation between the cathode and the plate, but also to act as a modulator. That modulation system enabled you to amplify a small signal that goes into the grid and turn it into a large voltage change between the cathode and the plate. So you can use it as a switch or as an amplifier. And in fact, it's a common fallacy that people think that a transistor is just a switch. Just because they're in digital design class doesn't mean everything is either on or off. Even though I'm a computer engineer and everything must be either true or false or on and off. In fact, transistors, this is a current-controlled current source known as a bipolar junction transistor, BJT, is actually an amplifier, which we operate in saturation in order to make it a switch. But there is a linear mode. So what we do is we look at current into the base, and then we look at the conduction and there is this linear mode in which we can operate. And if we operate during the linear mode, we can actually make this into a nice linear amplifier. Otherwise, it just slams into one supply rail or then into the other. Even other technologies known as the field effect transistors, which are little more than voltage variable resistors, have a gate, a source, and a drain, as opposed to a base, a collector, and an emitter. And so these things are voltage variable resistors. These things are current controlled current sources. Both of them can be used either as transistors or as amplifiers. Similarly, the vacuum tube could be used either as a transistor or, either used as a switch or as an amplifier. Can't use it as a transistor because obviously it's not solid state. It's got gas in it, which is, I guess, a fluid, I suppose. So then there's another thing that says triodes can't do high power. That's not true. They can do in fact, the voltages here will kill you. These are, 500 volts, 800 volts across the cathode and the plate. Very high voltages. The filament is relatively low voltage. That's around 6 volts AC. But the biases, the grid voltages, these are big time voltages, usually. We don't see that here in transistors. Transistor voltages are generally safe voltages unless you have some sort of a high power transistor. So hopefully that answers your question. It gives you a little more background about triodes. Any other questions about the midterm? Number 30. Okay, so multiplication. How does one do this problem? A couple of ways. You can do it the smart way, or you can do it the hard way. Let's do the smart way. In the smart way, someone says, what's this? 0. Base 2 times this. 1, 0, 1, 1. Base 2. So this number, that's 8, that's 4, and that's 1. 8 plus 4 is 12, plus 1 is 13. 8 plus 2 is 10, plus 1 is 11. And that gives me 143. So in other words, 13 times 11 is 143 base 10. And then someone says, is that going to be equal to 1, 0, 0, 0, 1, 2, 3, 4? Right? So what number is this base 2? Well, 1, 1, 1, 1, that's 15. And 2 to the 0, 1, 2, 3, 4, 5, 6, 7, that's 128. And 5 and 3, 3, carry the 1, that's 4, that's 143. And look, they're the same. If 11 times 13 is equal to this, base 110 was 143, then it looks like multiplication works. Now the other way you can do it is you can write 1, 1, 0, 1, 1, 0, 1, 1, and then write 1, 1, 0, 1, and then write 0, 0, 0, 0, and then write 1, 1, 0, 1, and then write 1, 1, 0, 1, and then you can add these things together. 1, 0, 0, carry the 1, 1 plus 1 plus 1 is going to be 1, carry the 1. Is there too many 1s in here? 1 times this is that. 1 times this is... Oh, I screwed it up, did I? 0. Then this should have been 0. little too fast. And then 1, 1, 0, 1. So now it's 1 plus 1. 1 plus 0 is 1. 1 plus 1 is equal to 1, 0, carry the 1. Boy, I really am messing up. And so, in principle, that will equal this. Aside from my blemish of not knowing how to multiply by 1. That's the dumb way to do it. This is the smart way to do it. So convert it to base 10, then take the output, convert that to base 10, and then see if the two multiplies it together correctly. Or you can just sit there and make all kinds of crazy binary errors like I just did and see if it matches. I could do this again if you like. Would it be better if I did it again? Nobody cares? Anyway, you haven't. Do it again. Okay, yes, sir. 1, 1, 0, 1. 1, 0, 1, 1. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. 1 times 0 is 0. 1, 1. Then we have 0, 0, 0, 0. And then we have 1, 0, 1, 1. There, I did it. I did it. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1, plus 1 is 1. Excuse me. Excuse me. I'm sneezing into the microphone. Did I do this wrong? No, actually, that came out good. How's that? That's clean. Any, gee, and I sneezed in between, too. Oh, excuse me. Any questions about this one? All right. Other questions about the midterm? Sure. Let's see what we can do here. All right. 7 minus 1 is 6. How do we do this using 2's complement, using only 4 bits? So the first thing you do is you convert 7 base 10 into 1, 1, 1. That's binary for base 10 version of 7. And then add the leading 0 because it says 4 bits. And you need the leading 0 because it's going to have to represent a positive number. And that 0 shows that it's positive. Then comes 1. 0, 0, 0, 1. That's a 4-bit representation of positive number 1. We convert that to 2's complement, and we get 1, 1, 1, 0. Then we add 1, and we get 1, 1, 1, 1. Now you take 1, 1, 1, 1, and you add it to 0, 1, 1, 1. Get 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is equal to 1, carry the 1. 1 plus 1 plus 1 is equal to 1, carry the 1. 1 plus 1 is equal to 0, carry the 1, which falls on the floor because you've got a 4-bit number. And now you're left with 0, 1, 1, 0, which is the binary representation for 6, and is a correct answer. How's that grab you? Is that good? Sure. Happy to do that. Any other questions about the midterm? There were no questions last time, and now we're filled with questions. No questions? Great. Time for characteristic equations. The characteristic equation for flip-flops, and we're going back now to chapter 6. I'm just going to write characteristic equations, CEs. can be described as follows. If you have the input D and the present state Q, you should be able to derive what the next state is, Q plus. D flip-flops say they're going to delay whatever the input is and make that the next state. And so with the D flip-flop, we see the next state is going to be 0, 0, 1, 1. And so we write the characteristic equation for the D flip-flop as Q plus equals D. And that's it. That's the characteristic equation. Let's do it again. Only this time, what we're going to do is we're going to write T and Q. Now, in this case, it's in the hold state. In this case, it's in the toggle state. In the hold state, Q plus is the same as what it was from before. It's the same as the present state. In the toggle state, Q plus is going to alternate. It'll toggle. So now we can look at Q plus and we can look at the truth table for T and Q, and we can say that Q plus equals, this is how you get the characteristic equation, what's the function for between T and Q that will give us Q plus? Well, that function is an exclusive OR. T exclusive OR Q, which is equal to TQ, or TQ. So it's T prime Q, or TQ prime. That is the characteristic for equation for the toggle flip-flop. Anybody got any questions about this? You're able to see that this truth table creates a, how you say, an expression for Q plus. Yeah, 0, toggle flip-flops behave in the following way. When there's a 0 on input to the toggle flip-flop, it does not toggle. It just goes into a hold state. But when there is a 1 on input into the toggle flip-flop, it causes its state to toggle. So if it starts in state 0, it goes to state 1. If it starts in state 1, it goes to state 0. So if you had a toggle flip-flop, Q prime, and you input a 1 with a little clock, you will have built a buzzer. And the buzzer will change from plus to minus, and minus, well, not plus to minus. It'll go 0, 1, 0, 0, 1. No, 0, 1, 0, 1, 0, 1 all day long. This is a buzzer. That's a buzzer. And so, from the point of view of what toggle flip-flops do, their behavior, they're in a hold state when the input is 0. They're in a toggle state when the input is a 1. Does that sort of make sense? All right, let's do it again. Only this time, we're going to use a flip-flop you've never seen before. This is called the JK flip-flop. And it too is divided up into sections. This is the hold state. This is the reset state. This is the set state. And now this is the toggle state. Notice if you put J and K together and you make them both equal to 1, it will start to act like a toggle flip-flop. But if you take J and K and you assert J to be 1 and K to be 0, that's going to set for the next state, Q plus. If you use the H for the hold state, both are inputs and they're both equal to the same thing and they're both 0, it does not change state. So if it started as a 0, it ends as a 0. If it starts as a 1, it ends as a 1. Reset, whatever state it's in, it becomes 0. Set, whatever state it's in, it becomes set. Toggle, whatever state it's in, it alternates to the inverted state. That is how the JK flip-flop is supposed to work. Yes. Yes, yeah, set is supposed to cause everything to set. Reset is supposed to cause everything to reset. Toggle causes the inversion of the present state to the next state as being the opposite of what it was. So if it starts at 0, it goes to 1. If it starts at 1, it goes to 0. And hold essentially says if it's starting at 0, it stays at 0. And if it starts at 1, it ends at 1. Did I answer your question? So now we can proceed to obtain the characteristic equation, but probably we need to use a K-map. So let's do that. We'll use a K-map. That's all right. I don't mind using a K-map. K-maps are okay. I think I remember how they work. Something like this. JK and Q 0001 1110. Changing colors. And then I'm going to number my truth table. This is my radix equal 10 column. And I have 1, 4, 5, and 6. And all the rest are 0. And so now that I have my K-map, I can write out what is Q plus. Using my K-map, I can obtain a minimum sum of products. So that's going to be J Q prime. And that's going to be let's see, J is changing, but it's K prime Q. Does everybody kind of see that? And normally we're used to seeing A, B, C. Here I've labeled it J, K, Q, but that shouldn't throw you too much. And that is the characteristic equation of the JK flip-flop. Pretty sweet, right? That summarizes this whole truth table using our good friend the K-map. Who got confused here? Anybody? Anybody get confused? JK flip-flops. JK flip-flops. So this is the interesting thing. What we have done here is we've derived the characteristic equations from the basic behavioral descriptions. Well, suppose we want to go the other way. Suppose we want to say that given the behavior that we would like, because we want to use these things for design, what inputs would be appropriate for, let's say, T? And for the T flip-flops, we know if we want to change from 0 to 0, we're in a hold state, so the input should be 0. If we want to change from 0 to 1, then we want to toggle. If we want to change from 1 to 0, we're going to toggle. And if we want to keep the state, we do the hold. And that is what toggle flip-flops will do if these are the design parameters that we want to see changes in. in comparison, the D flip-flop says, well, if you want a 0, you input a 0. If you want a 1, you input a 1. Want a 0, input 0. Want a 1, input a 1. And you can see the D flip-flop has changed quite a bit. Now let's take a look at something with two inputs. This is the JK flip-flop. JK flip-flop is different. What we said before was, see if we can bring it up. Oh, maybe you know what I'll do? I'll just rewrite it because that makes it more clear, I think. JKQ Q plus. So now we group. We call this the hold, the reset, the set, and the toggle. Because it's in a hold state, we just copy over. Because it's in the reset state, we set to 0. Because it's in the set state, we set to 1. Because it's in the toggle state, we take whatever the present state is and we invert it. So that's fine. Now let's go back. We're going back now. If you want to go from 0 to 0, what do I need? Well, I can use 0, 0, or I can use 0, 1. Right, I can do either to get from 0 to 0. As a result, I have 0, don't care. Does everybody kind of see that? There's two ways in which to go from 0 to 0. You can either, right, because if you're in state 0, you could be in the hold state, and that'll keep you in state 0. Or you could go to the reset state, and that will set you to state 0. So since this can be either a 0 or a 1, we don't care what it is. And those don't cares are going to help us when we do our K-maps. So then if we do the search again, I want to change colors, and I'm looking for things that will cause transitions from 0 to 1, I find that is here, and I also find it's here. And there's two ways to do it. It could be a 1 and then an X, right? Because if it's in state 1, it's in state 0, and we want it to go to a 1, we can put it into the set state, so that could be 1, 0. Or, because that changes the state, we could say, hey, it could be a toggle. So we'll put in 1, 1, and that's okay too. So if it could be 1, 0 or 1, 1, then it's 1, don't care. Let's try that one more time. This time we're going to do a change from 1 to 0. Right, that's in here. 1 to 0. So how do we do that? Well, that's here, and it's here. And so going from 1 to 0, here and here, means we got our choices. We can either input 0, 1, which puts us into the reset state, or we can do 1, 1, which puts us into the toggle state. And so that means we have a don't care 1. So here's don't care 1. And now, let's look at the 1, 1. Here's 1, 1. Let's pick a different color. Colors. Yeah, I don't know if you could see this color. That's 1, 1. And this is 1, 1. Can you see that color? I guess you can. So this one says, yeah, it's a lousy color. Let's do this again. I can have 0, 0, or I can have 1, 0, which means, putting these two together, it's don't care 0. We're going to write this in pen. Don't care 0. Don't care 0. This is the remapped excitation table for 3 different flip-flops, one of which you've never seen before, and is twice as complicated to design as either D or T because it has 2 inputs. two inputs. Two inputs, no waiting. And that is your remapped excitation table. And you can see that for the sake of argument on chapter 6. Let me grab this. I'm grabbing a look into the book so that you can see where we have all of these good things. Because the book, once you get into it, actually is kind of useful. So here is your characteristic equations. We did the D flip-flop, we did the JK flip-flop, and we did the T flip-flop. But what we haven't done yet is the RS flip-flop. I'm saving that for later. And then, let's see if I can get this underneath the camera. Over in here, and it's kind of small actually, but you can see Q plus, and here's the JK 0x, 1x, x1, x0, which is 0x, 1x, x1, x0, right there. And I just derived it for you. So that's on page 308. That's where we're at. 308. So you definitely want to get up to there in your reading, because that's where we're at. That's kind of where the lecture is. And so now, if you recall, we were busy designing counters. Can anyone remember what to do in order to do counter design? Tyler, I want to design a counter. 0, 1, 2, 3. Using JK flip-flops. Can you start me off? Alrighty, so we'll do a present state, next state diagram, and we'll have A, B, and then we'll have A plus, B plus. Can you help me fill this in, Tyler? This is state 0. What's my next state? Yeah, what's the next state from 0? That's 1. And then from 1, what's the next state? There you go. And then from 2, what do we got? And from 3, where are we going? 0. That's all right. So then, now I need the remapped excitation tables for J sub A and K sub A inputs. J sub B, K sub B, right? This is interesting because we want to go from 0 to 0. It says here to go from 0 to 0, we use 0 don't care. To go from 0 to 1, we go from 0 to 1 using 1 don't care. To go from, oh, I've missed the line here. Just a moment, please. Now to go from 0 to 1, it's 1 don't care. To go from 1 to 0, it's don't care 1. To go from 1 to 1, it's don't care 0. To go from 0 to 1, it's 1 don't care. And to go from 1 to 0, it's don't care 1 and don't care 1. So that's cool. That's cool. That's cool. So it's, according to this, J sub B equals K sub B equals 1, which means B is alternating between 1 and 0 because we've made a buzzer. And then over in here, K sub A is equal to B. And then J sub A is equal to looks like you can make it equal to B as well. Because B is going to be 0, 1, 0, 1, and we don't care what that stuff is, but that'll be 0, 1. And here, if it's B, it's going to be 0, 1, we don't care, and then 0, 1, which looks fine. So now, to build this little counter, J sub B equals K sub B equals 1. K sub A equals J sub A equals B. The implementation was really simple. I don't know if you remember, but when we wanted to do the same thing with the D flip-flop, we were building an exclusive OR gate. But we don't need that with the JK flip-flop. We got a simpler implementation, even though it was a more difficult design. With a more difficult excitation table. And if you think about it, you can compare implementations now. Let's assume we went to a D flip-flop. We'll call it D sub A and D sub B. Right? And then we just write out 0, 1, 1, 0, because that's what we have for next states, and 1, 0, 1, 0. So now it's clear. D sub B is equal to B prime, so that's okay. But D sub A has got to be A exclusive OR B. So what that means, to me, the designer, is that D sub A needs A, B, an exclusive OR gate, and D sub B is just going to be equal to B prime, which I can obtain from here. So that's a more complicated implementation than the JK flip-flop because of this extra gate, which will cause not only additional cost, but additional delay and make everything slower. So now you have seen JK flip-flops, D flip-flops, T flip-flops, remapped excitation tables for T, D, and JK, as well as counter designs for T, D, and JK flip-flops. How's that? Now, three, 1, 2, 0. This is a counter. Even though it's not counting in any particular order, it's a counter. Given the following finite state machine description of a counter, find an implementation using toggle flip-flops. That's a perfectly legitimate question which could easily appear on the final. Why don't you take a few moments and see if you can figure out how to do that. I'm going to take about 30 seconds and grab another cup of coffee. I'll be right back. Okay, I'm back. Who has an answer? Well, who can get me started? Okie doke. So we got the present state, next state table. What comes after 0? Goes to 3. 1, 1. And what comes after 1? 2. There you go. And after 2, goes to 0. And after 3, goes to 1. So that's good. And now we need to know the remapped excitation table inputs for T sub A and T sub B. So you guys help me. What do I write here? They're both changing, right? A is changing to 1, B is changing to 1. What should the inputs be if you want the present state to change? Yeah, everything should be a 1. 1 and 1. And now it looks like everything's changing again. So it's 1 and 1. And now it looks like there's only one change at the most significant bit. And here there's only one change in the most significant bit. Looks like T sub A is equal to 1. What's T sub B equal to? Yeah, A prime. T sub B equals A prime. So now my implementation T sub A equals 1. T sub B equals A prime. And now I've got my wacky little counter that goes 3, 1, 2, 0, 3, 1, 2, 0 all day long. Well, here's A, 0, 0, 1, 1, and here's T sub B, 1, 1, 0, 0. So if we look at these two different things, they are identical except they're inverted in sense. Does that sort of make sense? Here. I did it by inspection. I suppose doing these things in my head isn't such a great idea, but maybe you could see how I compared these two and said, oh yeah, that's A prime. And that's it. Now, here's the tricky bit. The tricky bit. Suppose you wanted to re-implement this with JK flip-flops. It's going to change your implementation somewhat, and you're going to need your remapped excitation table One thing I can say about J and K is it's symmetric. Other than that, you're just going to have to write it down or look it up or rederive it as I have done. Now, remapped excitation table. It's tricky, right? We've gone from 0 to 1. Oops, 0 to 1 and 0 to 1. So going from 0 to 1 means 1x. Zero to 1, 1x. 1 to 0, that's x1. 1 to 0, x1. 1 to 0, no, yeah, 1 to 0, x1. Here's 1 to 1, it's x0. 0 to 0, that's 0x. So now JA, KA, they could equal each other and equal 1. Yes. Well, open book, open notes. You don't have to memorize it, and I give it to you in the beginning of homework 8, and it's in the book. So you can always look these things up, or you can rederive them. I don't recommend memorizing it. It's not easy to do. Just look up the excitation table. It's easier. So JA equals KA, and they both equal 1. Looks like K sub B could be written as could be 1, 1, 0, 0. And if that were the case, you could make K sub B equal A prime. And then over in here, you could write it as 1, 1, 0, 0, which would be also equal to A prime. Right, because if this were 1, 1, 0, 0, it would fit with both don't cares. So that's my slick willy way to deal with it, such as it is. And so the excitation tables didn't result in a much simpler implementation. But if you think about it, wiring J and K together makes a toggle flip-flop. And so what he did was we wired J and K together, and we basically treated it as a toggle flip-flop and wired it up to A prime. And we wired J and K together over in here and wired it up to 1, and that created a toggle flip-flop. So in fact, toggle flip-flops can be created from JK flip-flops just by wiring J and K together. That's pretty cool, isn't it? So by direct analogy, you were able to obtain an implementation that was identical in complexity to the toggle flip-flop in this particular case. That won't always be true, but there it is. Any questions about what I just did here? Kind of went over a lot, I thought. Sort of interesting. Let's see what else we can do. So now, what has happened? Oh no, something awful. Something awful. Present state, next state. I need more bits because I'm counting up to higher numbers. Now, from state 0, my next state is 10. From state 1, my next state is 0. From state 2, my next state is going to be 1. From state 3, my next state is supposed to be 2. From state 4, my next state should be 3. From state 5, my next state should be 4. From state 6, my next state should be 5. From state 7, my next state should be 6. From state 8, my next state should be 7. From state 9, my next state should be 8. From state 10, my next state should be 9. From state 11, what should I do? Don't care. I mean, if you want to make a counter that, if it starts in one of these sporadic states we don't care about, ends up in state 0, to resume the count, you would create what's known as a self-starting counter, and you could set everything to 0. But if you really don't think you're ever going to be in any of these states, then just make them all a bunch of don't cares. Setting them all to 0 might be okay if you started in state 15 by accident when you powered on, it went to 0 and resumed the count. But if you really don't care, then leave it as a don't care. Now comes the implementation. Let's pick D sub A, D sub B, D sub C, and D sub D, I guess. D sub D. So now I can just copy over. And now you need 4K maps. And the 4K maps will give us, yeah, go ahead. Because the characteristic equation is equal to D for the D flip-flop, right? Because it's a delay flip-flop. If what you want is a 1 in your next state, then you have to put a 1 in on the input. Because the D flip-flop is little more than a latch, which simply latches the input on the next clock cycle. Does that answer the question? If it was T flip-flops, we'd be saying, oh, A is changed, so we put a 1 in here, and if B is not changed, so we put in a 0, and C has changed, so we put in a 1, and D has not changed, so we put in a 0. So the first row would be the same, but eventually the rows would start to change. But with D flip-flops, we know that the inputs have to equal whatever we want for our next state, because they just latch. They act as a delay. D is for delay, by the way. Did I answer the question properly? I'm not sure if I answered. That's okay. So, what's next? Well, I don't know. I guess it's time for K-Map City. Now you know why you have to learn your K-maps. Zero, 9, and 10. Oops. And don't cares for 11 through 15. And you can see how the don't cares may be helping us quite a bit. Because of those don't cares. I can loop this. And that'll give me A, C. And because of the don't cares, I can loop this. And that's going to give me A, D. This little guy in the corner, I got nothing for him. So when I loop it, it's like that. And so that is D sub A. And this is the expression that would need to be implemented for D sub A's input. And now you got to do 3 more K-maps for the 3 more, for the other 3 D flip-flops. What do you say? Want to give that a try? You guys tell me, what do you think D sub A should be? I'm sorry, D sub B. You do some K-maps. Watching me do K-maps can make you tired, but you won't get the benefit unless you do them yourself. It's kind of like those ab exercises. You can watch them on TV, but they won't help your abs unless you do them yourself. Any questions about what I've done so far? Who wants to tell me, what is D sub B equal to? You guys still working on this? Hurry up. Take your time. Hurry up. It's not good for you guys to just sit there and watch me do these exercises. You've got to try them yourself. Any progress? Anybody stuck? Sure. So I filled out this K-map using the column through here. So once I knew the function for d sub a, and I filled out the column into the K-map, I did my looping to obtain the minimum sum of products form, which is needed for d sub a. And that will be the foundation for the implementation for the combinational logic used to drive that bit of the counter. Yeah, you need to go d sub b, fill out your K-map using d sub b, loop your K-map, and get a minimum sum of products form implementation on d sub b. Having said that, you could probably do it with a an A21 multiplexer if you like. All right? If you did it with an A21 multiplexer, how cool would that be? What you would do is you divide it up into rows of 2. This would be input 0, and then what you could do for d sub b, I mean, this is a really slick way to go. Call this d sub b, and now input 0 is actually equal to 0. You see b is 0 here, and it's 0 over there, and it's equal to d over in here, and then this would be 0, 1, 2, 3, 4, 5, 6, 7. Input number 3 would be equal to 1. Input 4 would be equal to d prime. Input 5 would be equal to 1. Input 6 is don't care, and 7 is don't care. Just make them 0. So it's easy. And then you don't need any K-maps at all. How's that strike you? So that's a slick way to do it. Super slick. Super slick. We could do that twice, actually. I like that. It's really cool. Right? Because now I don't need to use K-maps. No K-maps are harmed. 0, 1, 2, 3, 4, 6, 7. D sub c. And d sub c is equal to d prime, number 1, D sub c is equal to D. Number 2, D sub c is equal to D prime. Number 3, D sub c is equal to D. Number 4, D sub c is equal to D prime. Kind of nice and symmetric that is. 5, it's going to be 0. And 6 and 7 will all be 0. And there's D sub c. And this is all done with an 8-to-1 mux. No K-maps. No K-maps. And now I could do D sub D, but I can leave that as an exercise. Now that you've seen how to do them, you can do your own D sub D. I think that's good. Right? Because here it's equal to 0. Here it's equal to D prime, D prime, D prime, D prime, D prime if you like, and then just 0. In fact, you could make it all, since it's don't care, so you could make it all D prime. In which case, yeah, how easy is that? Right, so this would be 0, and all the rest D prime, and then the output is going to be D sub D. The input to the D component of the delay flip-flop. And that's a cool way to do it. Very cool. And that's what I have for you for today. Are there any questions? So we've implemented, very cool, a 4-bit counter using D flip-flops, 8-to-1 multiplexers, K-maps, and don't cares. And we can count down from 10 to 0. So when your parents say, "What did you learn today?" You say, "Oh, I learned how to count down from 10. And I'll say, "What are we paying them for? Oh my God, what a waste of time." So there you have it. Counting in digital design. K-maps, be there or be square. Enjoy the rest of the day. Thank you for your attentions, and if you have any more questions about the midterms, please bring them with you for your class Thursday next. I will continue to entertain questions about the midterm. Enjoy the day. Thank you. Bye-bye.